Good day, everyone. I hope you're all doing well. Today, we are going to begin our series on integration. These videos are mainly for the students who have already learned the basics of integration at their intermediate level and are now in the first year of the university. But don't worry, if you're still in the intermediate and want to get ahead, this video can still be very helpful. Now, I expect that you're already familiar with the basic integration formulas. We won't be starting from the absolute basics or the baby steps. Instead, we will build on these formulas and go further. Before we dive in, let me quickly explain the method we will be using in this series. Instead of using the usual substitution method, where we always took the variable u, I will be using a visual approach. We will use a rectangle, which I'll be referring to as a box, to highlight the part we want to focus on. Then, we will differentiate what's inside the box, and the remaining part will go inside an ellipse. Thus, if there is going to be a question, I'm going to be encapsulating it inside a box. And after differentiating whatever is inside the box, we will get the remaining part in the ellipse. After that, we'll set that apart, or as I like to refer to, throw it in a bin, and apply the basic integration formulas to what's left. Let's make it clear with a few examples, and let's start with example 1. Take a look at the example 1 we've got here. We need to integrate this fraction. Now, if we put the box around the denominator, we don't get what's inside the numerator. To show this, box equals to x squared minus 9x plus 1 out of 1 by 2. And differentiating box gives us this result, 1 by 2 minus 9x plus 1 out of negative 1 by 2, 2x minus 9, which is in the desired result because it is not giving us this numerator, just 2x minus 9. This means we cannot use the logarithmic integration formula here. So we'll be trying a different method. Notice that inside the square root, if we differentiate what's in the under root, we do get the numerator, which is 2x minus 9. That's a good sign here. So taking this, we will be taking the inverse of the denominator and writing the whole expression as 2x minus 9 and x squared minus 9x plus 1 to the power of negative 1 by 2. Now we can apply the power rule for the integration. But before that, let's go over an important rule. You're not allowed to integrate the operator, which is the power to the power of negative 1 by 2, unless the differentiation of the box is present outside the operator. So, once that condition is met, three things will be removed. The integral sign, which is this one, the differentiation of the box, which we will be encapsulating inside the ellipse, and the d of x, this one. And then we are ready to integrate the remaining part using the power rule. Now let's continue with this example and finish it up. We will be taking power as the operator here. Let me do it with a red pen. Power as an operator here. This is going to become a box. The differentiation of the box is going to be 2x minus 9. Its answer encapsulated inside an ellipse. And eventually, we'll be removing the integral sign, the differentiation of the box, and the d of x, applying the power rule over the box. This means x squared minus 9x plus 1 to the power of negative 1 by 2 plus 1 all divided by negative 1 by 2 plus 1. This is the final answer we'll be getting, but don't forget to add plus c, because if we forget adding this plus c in the final answer, this will be a grave mistake. In the next few examples, we will follow the same method for solving the different types of integrals. Now, let's do example 2. In this example, we also have to integrate a fraction. So our first step should be to look at the denominator and placing it inside the box. We can see that the differentiation of the box is not found in the numerator. The differentiation of the box is going to be 1 by 2, 8x minus x squared, 8 minus 2x, which is not found in the numerator. Next, like we did before, in the previous example, we can check if the differentiation of what's under the square root matches the numerator. But we can see that is not the case here. It is 8 minus 2x that is not found in the numerator. So let's take a different approach. We can see that we can simplify this expression using completing the square method. So let's do working with 8x minus x squared separately and perform completing the square method on it, referring to this as W1, meaning working 1, 8x minus x squared. Taking negative as common, x squared minus 8x, x squared minus 8x plus minus 4 squared minus 4 squared. X minus 4 whole squared minus 16. Expanding the bracket, 16 minus x minus 4 squared. Now we'll be substituting it back to our original expression. Now, if you remember the basic integration formulas, this matches the form used for the sine inverse integration. I've written it separately to make it easier for us to identify this form, where a is the constant, the box is the expression that we are differentiating, and this is differentiation of the box. Once this is done and these conditions are satisfied, we can apply the sine inverse box divided by a plus c. So let's identify the box here in our expression. We treated x minus 4 as box, and the differentiation of the box is 1. In the numerator, we have 1, so we can remove these 3 things in the next step. Here, we have a constant 16, but there's no squared here, so we'll be taking the under root of the 16, which gives us 4. Thus, we'll be writing it as 4 squared. That is the same as a squared. Since these conditions have been met, we can apply our sine inverse formula and write the final answer as this. Sine inverse box divided by a plus c. Now let's move on to the third example. In this example, we'll be expanding a power using trigonometric identity. We are given the expression secant x plus tan x whole squared, and we have to integrate it. The first step is to expand the expression, and we achieve this. Secant square x plus 2 secant x tan x plus tan squared x. Now, let's think logically. We know that the integration of secant square is tan of x. So we'll be taking a look at tan squared x expression here and recall the identity, a trigonometric identity which relates tan squared and secant square. That identity is tan squared x plus 1 equals to secant square. Making tan square the subject, tan square is equal to secant square x minus 1. Now let's substitute it back into our original equation and continue with the integration.
So,
Now let's simplify the expression. This will be giving us 2 secant square x plus 2 secant x tan x minus 1. Now let's integrate term by term. This is going to give us 2 integral secant square x d of x plus 2 secant x tan x minus 1 d of x. The integration of secant square is going to be tan of x, and the integration of secant x tan of x is going to give us secant x. Now let's write it in neat form. So it is going to be 2 tan of x plus 2 secant x minus x plus c. This is our final answer. Let's take a look at example 4. In this question, we are asked to integrate the expression under root of 1 plus cos 4x d of x. Now, whenever we are given an expression that includes a square root or under root, the goal is to simplify it in a way that removes the square root. In trigonometric integrals, like this one, we often do that by using the trigonometric identities. So let's start simplifying. Just like in the previous question, we are going to take this as the working one and start doing its working separately. So, working one, let's just copy paste it here. To handle this, we'll use a trigonometric identity that helps us simplify the expression involving cosine of double angles. One of the identities which we can use is cos 2 theta is equal to 2 cos square theta minus 1. In our case, we have been provided cos 4x. So let's rewrite this expression in a way that is easier for us to understand. So cos 4x equals to 2 cos square 2x minus 1. Notice that if we make this the subject of the equation, we get what is the original expression in the under root. So let's make 2 cos square 2x the subject of the equation. So 2 cos square 2x equals to 1 plus cos 4x. Now let's go back to our original expression and substitute 2 cos squared 2x here. So to rewrite this, 2 cos squared 2x under root d of x. We can rewrite this as under root 2 cos squared 2x and then d of x. We can now successfully eliminate the under root like this, which is going to be leaving our original expression as under root of 2 cos of 2x d of x. Now let's integrate cos 2x. To do this, we treat 2x as a box here, and we take cos as an operator. We know that the integration of the cos gives us sine. However, when we take cos as an operator, and place 2x in the box. The differentiation of the 2x is going to be 2. We will be introducing 2 here, and outside the integral sign, we will do it like this. Eventually, we'll remove the integral sign, the differentiation of the box, and the d of x. Putting it all together, we are going to write our final answer as under root 2 divided by 2 sine of 2x plus c. Now let's go through this example 5 together. Here, we have to integrate a fraction once again. However, if you observe closely, the fraction is an improper rational fraction. This means that the degree of the numerator is greater than the degree of the denominator. The degree of the numerator is 2 and the degree of the denominator is 1. So before we can integrate, we need to simplify this expression. The standard way to deal with an improper fraction is to rewrite it as quotient plus remainder over the divisor. So let's break it down step by step. First, we are going to be dividing the numerator by the denominator. Now let's perform its polynomial division separately. Three x squared minus 7x divided by 3x plus 2. First, we are going to be dividing the leading term of the numerator, which is 3x squared, by the leading term of the denominator, which is 3x, which gives us first quotient of Q1 equals to 3x squared divided by 3x, that is equal to x. The first term of the quotient is x. Now multiply x by the entire denominator, which is 3x plus 2. This is going to be giving us 3x squared plus 2x. Subtracting, it is going to be giving us 0x squared minus 9x. X divide minus 9x with the leading term 3x. So equation 2 equals to minus 9x divided by 3x. That is going to be giving us minus 3. Now multiplying minus 3 with the entire denominator, which is 3x plus 2, gives us minus 9x minus 6. So it is going to be 0x plus 6. Now you're going to write our final answer here as a quotient plus remainder over divisor form. The quotient is x minus 3, the remainder is 6, and the divisor is 3x plus 2. So x minus 3 plus 6 divided by 3x plus 2. Integrating our entire expression. Now if we integrate x, it is going to be giving us x squared divided by 2. The integration of minus 3 is minus 3x. And let's integrate this fraction separately. Taking the denominator in the box, the differentiation of the box is going to be 3. So we adjust for this by introducing and balancing the factor of 3. And we are going to remove the integral sign, the differentiation of the box, and the d of x. So we are going to be writing our final answer as this. The 6 divided by 3 yields 2, ln 3x plus 2 plus c. This is our final answer. We are given the integral 3x plus 2 divided by under root of 1 minus x squared. Here, the integrand involves a fraction, and the denominator involves the under root. So our goal is to integrate this expression step by step. Just like we used to do before, step by step, we are going to take denominator in a box and see if the differentiation of this box is found in the numerator. The differentiation of the box is going to be 1 by 2, 1 minus x squared, power of negative 1 by 2, negative 2x. That is equal to negative x divided by under root of 1 minus x squared, which is definitely not found in the numerator, which is 3x plus 2. So we cannot apply the logarithmic rule here. Next, we are going to see that what's inside the under root is found in the numerator. Taking this in the box, the differentiation of the box is going to be negative 2x, which is not found in the numerator. So we cannot apply the power rule here as well. Since the direct methods aren't helping, let's try breaking the integrand into simpler parts. We can do that by separating the fraction like this. It is going to be giving us 3x divided by 1 minus x squared plus 2 divided by under root of 1 minus x squared. Now, let's focus on each term separately. We are going to be considering this as our first working. I'll denote it as W1, and this as the second working. I'll denote this as W2. Now, let's go back to our direct methods we used to apply before and take the denominator in the box. We know most definitely that the denominator of the box is not found in the numerator. We have done its working above. Now, let's take what's under the square root and see if it's found in the numerator. Taking 1 minus x squared in the box, the differentiation of the box is going to be minus 2x. So let's carry out this integration by applying the power rule. We are going to rewrite it as 3 integral x 1 minus x squared power of negative 1 by 2 d of x. Now, when we take power as the operator and the differentiation of the box we know is minus 2x, we are going to introduce a balancing factor, which means minus 2 here as well, and outside here as well. Removing these three things, the integral sign, the differentiation of the box, and the d of x, we are going to integrate this using the power rule and get the final answer as 3 minus 3 divided by 2, 1 minus x squared, power of 1 by 2, all divided by 1 by 2, plus c1. Simplifying this expression, this 2 and this 2 is going to cancel out. So we are left with the final answer as minus 3, 1 minus x squared, to the power of 1 by 2, plus c1. Now let's integrate this second term as well. We can see that the integrand matches our sine inverse integration formula, if you recall from the basic integration formulas, where this is a box squared and the differentiation of the box equals to 1. So we can see that this is a box and the differentiation of the box, if found in the numerator, can allow us to write our final answer as sine inverse box divided by a plus c. So we'll be carrying out this step here to sine inverse box divided by a, which is 1, plus c2. Now that we have done the working 1 and working 2, we are going to be substituting it back into our original expression and write the final answer. Now to write it neatly, we can see that we have got two constants c1 and c2. We can assume that c1 plus c2 equals to c. Writing its final answer in the neat form, we are going to do this. And this is our final answer we have achieved here.